Okay, and finally, last video, remember that it's in our interests when we're generating electricity and we're sending it to people's houses, it's in our interest to change the voltage. Okay, a power station will be able to produce a certain amount of power in watts. That's a certain amount of energy per second that it can produce. Typical power station might be talking about 500 megawatts. That's 500 million joules of energy per second being transferred, and you want as much of that energy to get to people's houses or to get to businesses and factories as possible. So if we increase the voltage for that power, P equals IV, that means we're going to decrease the current. Increasing the voltage decreases the current. Less current means less heating effect in the wires. So here what I have is I've got two coils, okay, 1, 2. Now if let's use plenty of loops on each one. If I have a direct current and I put current through this wire, I get a magnetic field produced, but that magnetic field is stationary. It's not moving. Okay. If I change that magnetic field in the opposite direction, opposite magnetic field, but again it's not moving. It's when I made that change, the bulb lit up ever so slightly. You see it? So if I were to have a magnetic field that's moving backwards or forwards, changing, or the current was changing, then the bulb would light up. So let's switch to alternating current. So here in my power station, in my generator, I'm producing alternating current. So the magnetic field is moving backwards and forwards. Let's get rid of the field and let's pop a compass, because you can see it a bit better if I have a compass. So we've known from before that if I have fewer loops here, my magnetic field is not as strong. So I get less of a magnetic field in this loop here. If I make more loops, then I get stronger magnetic field. Now, what's happening is, because the magnetic field is moving backwards and forwards, when I bring these two loops close together, this loop produces a magnetic field, and this loop has inside it a magnetic field that's changing direction. So left-hand rule. Okay. On the producing side, the generator side, I have a field that's moving, generates current. Sorry, no, getting that wrong way around. On the side where I've got my generator, I have on this side current moving, producing a field. On the opposite side, I have field moving, producing a current. Okay, so what we need to see is there is a formula that we use, okay, which links the number of coils on each of these sides. This is what we call the primary coil, this is what we call the secondary coil, because this is where the energy goes in, this is where the energy comes out. Switch to voltmeter so we can see a bit better. Now, of course, if I bring these closer together, and I even put them inside each other, okay, here I'm seeing more of an effect. The inner coil produces a magnetic field because it has current coming from the generator. The outer coil has a current because the field from the inner coil is moving and it's producing a current. Okay, now the important thing here is voltage and loops. Okay, if I have few loops on the inner coil, I get a weaker field and I get less voltage on the secondary coil. If I increase the number of loops on the inner coil, I have a stronger field, so I get more voltage on the secondary coil. Here on the secondary coil, if I reduce the number of loops, having less loops in the field means less voltage, and here having more loops in the field means more voltage. Okay, and so the formula that we're going to use for all of this is the number of loops on the secondary coil divided by the number of loops on the primary coil is equal to the voltage on the secondary coil divided by the voltage on the primary coil, which is in the exercises that I've given you to do. Okay, so transformer is two coils close together. Okay, primary coil is where alternating current goes into that primary coil, and then secondary coil is where an alternating current comes out of that coil. And one of the best examples of this is if you have an electric toothbrush. Okay, you have electric toothbrush which needs to charge up. Okay, if I just pause a second, I'm going to nip and get my electric toothbrush to show you. So, as we should know, plastic is an insulator. So this is the piece of my my toothbrush charger that I plug into the power supply. Does not have an earth pin, doesn't have an earth connection. So if I look at it closely, somewhere I should see the symbol. It's just there for double insulated, which means it has a plastic case. Inside my toothbrush I have a battery that needs charging, so chemical cell that needs charging with energy. How does this work? Plastic, a plastic covered stick, plastic, put that on top of that, I plug it in, but the electrical current cannot be passing through this plastic into my toothbrush. What's happening is, here I have a small coil, alternating current, here I have a bigger coil, so that small coil goes inside the bigger coil, and the same as a transformer, well, it is a transformer, same as a transformer that we're seeing on the screen there, is that the field produced by the electromagnet here is moving inside the coil that I have here, and that's inducing is a word to use, it's inducing current in the coil that I have here, and that current is then used to charge up the battery cell. So transformers, we use it to change voltage, but also we can use it for charging a battery cell without actually having a physical metal connection between the two objects. So toothbrush, those of you that have telephones that can share charge, I don't, I have a cheap one, exactly the same. It's a magnetic field that is transferring the electrical energy. There's no electrical connection. The only limitation on this is that they have to be close together. Doesn't work at large distances because the field spreads out. Okay, so that is more than enough for your notes and what you need to know for this topic. Let's get on to radioactivity.